So in this example, it is used LMTD method. Let me read the problems. The hot fluid inlet enters the heat exchanger at temperature of 90 degrees Celsius. So this is the hot fluid, and leave at 70 degrees Celsius. Okay. The cold fluid enters the heat exchanger at 25 degrees Celsius and leave at 35 degrees Celsius. Calculate the LMTD value if the double pipe heat exchanger is operated under parallel and counterflow configurations. Which configuration is more efficient? So the very first step to analyze the problem is to make a basic illustration of the heat exchanger, which we have here. So in the first here on the left, it is the parallel flow. So parallel flow means both hot liquid and cold liquid move to the same direction. So on the left side here, this is the inlet, and on the right side this is the outlet. Okay, and then the condition of the feed and the condition of the hot fluid and cold fluid is given. So in this case, we are asked to find out the LMTD. So LMTD is delta TO, which is the O here is always to the hot side. Okay, the inlet of the hot fluid. Okay, so it is always the the inlet of the hot fluid, and then conversely, the TI here is always to the outlet of the hot fluid. So this is hot, and this is hot fluid. Okay, that you use as reference. And the next step is quite easy. You go into the equation, you key in all of the number, and we end up with logarithmic mean temperature difference equal to 48.46 degrees Celsius. So how about the other configuration, the counterflow configuration? You see, counterflow configuration means that the hot fluid and the cold fluid goes to the opposite direction. So in this illustration counterflow, the hot fluid goes to the right. So this is hot fluid, and the cold fluid goes to the left. So this is cold fluid. And of course, then delta TO then here equal to the one on the left. We always refer to the hot. So it's a 90 minus 35, and then delta TI here is on the outlet of the hot fluids, which is then 70 minus 25. So what we do next, we apply the equation for logarithmic mean temperature difference, and finally we key in all of the numbers, and then we end up with the logarithmic mean temperature difference equal to 49.83. So what it says is that because if you remember, Q equal to UA delta T, QA LMTD, right? So what does that mean is that if I use a counterflow, I will always have a better performance. For the same Q, since my delta T is higher, I can have a slightly smaller area of the heat exchanger.